In class, we are going to look at the investigation, How to Survive a Zombie Attack. And the investigation goes something like this. On June 30th, 2035, a sleeper cell of zombies executed an evil plan 10 years in the making, their objective to turn the entire human race into evil zombies. Each zombie can turn 3 humans per day, but they are not sure how long it will take them to completely turn every human on the planet. Complete the table below to show how many total zombies there will be every day for the first 10 days of the attack. The original sleeper cell had only 5 members, but keep in mind that the newly turned zombies also have the power, and they will, to turn other humans. Alright, so when reading through a word problem, you should underline the important information, and this is pretty important. 3 humans per day, and that they start with 5 members. In class, you'll fill out the chart. So example, number of zombies each day, 5. And then we're going to go all the way up to 10 days and see if you can write the equation. So the next day would be 5 times 3, which would be 15. The next day it would be that 15, or that 5 times 3, but then times another 3, which would be 45. And the next day it would be that 5 times 3 times 3 from the day before, which would be, and then times another 3. And that would be 135. And so you can see each day we're multiplying by 3 more. And then see if you can find the pattern for X days. Well, if you look for day 1, it was only 1 3. For day 2, it was 2 3s. For day 3, 3 3s. So when we have day X right here, it'd be 5 times 3 to the X power. What patterns of growth do you notice in the number of zombies turned each day as the days go by? Well, you can see it's being multiplied by 3 for every day. What would this look like on a graph? So again, we can scale our graph right here, but I'm going to just graph my equation so we can see what this looks like. Okay, so I pull my graphing calculator. Let's add a new graph page. Let's see what this graph looks like. So it'd be 5 times 3 to the X power. And I'm going to actually zoom up my window. And let's change our settings. Let's go from day 0 to 10. Let's make our minimum 0. And let's make our maximum go up a lot more because it was pretty high. Let's go up to like 300,000. And when we graph it, we can see it will look something like this, that it starts up pretty slow, but then by that 10th day it increases quite dramatically. How many zombies are turned on day 10? So for this you can use your table to figure it out. What would you have to multiply this number by to get the number of zombies created on day 11? So again, you can figure that out with a pattern.
The 9th grade bar team meeting is happening at this time in C350.
How would the entire table change if instead of starting with 5 zombies, we only started with 1? Well, you can see where the 5 is every time, and that would change into a 1. And you could try those numbers and see what would happen. And then D, how long would it take for zombies to take over the world? Assume the population of the world is 6,975,000, and we only start with 5 zombies. So that one we'll try in class. And then number 4, which of the equations below would correctly model the number of zombies turned each day if you start with 5 zombies? And so we looked at that equation, and the accurate equation would be this one right here. What does the unknown variable x represent in the equation you chose? So this x represented the number of days that have gone by. Write an equation to model the pattern if instead 12 zombies were in the sleeper cell initially and had the ability to run, so they can infect 6 zombies per day. Alright, so this would be y equals, we're starting with 12 zombies, and it goes up by 6 per day. So here's what the equation looks like. And there's several ways that you can solve this. We can set this equal to our 6,975,000,000. And see when this equals 12 times 6 to the x. You can use a guess and check. You could try it in your table. You could graph it. Number 7, if you were given the choice between more initial zombies but a slower growth rate, or fewer initial zombies but a greater growth rate, which would you choose and why? So that one, again, is something to think about, and we'll discuss it in class. So the next part says, within 3 days of the initial attacks being reported, a group of scientists quickly began working to find an antidote for zombieism. Within a few short weeks, they were successful, but unfortunately, their antidote was found to be only successful 15% of the time. This means that from the previous round, 15% will not remain as zombies for the following round. Make a table showing how many zombies were cured after 10 rounds. All right, so if there's the 6,975,000,000, but the next day 15% are cured, you have to think of how many zombies are remaining, and if 15% are cured, then if we take 100% minus 15%, then 85% of the day before remains. So we can multiply this by 85%. So the next day there's going to be 5,928,750,000. And each day, again, we're taking 85% of the day before because 15% are cured, but 85% are still zombies. And so you can finish that table by multiplying by 85% a day. What patterns of decay do you notice? And again, we talked about this as 15% are cured, 85% remain. We can see what the graph looks like. Again, if you get the table and you graph it, you can see it's going to go down. And then write an equation to model it. So again, we start with our initial value. 6,975,000,000. And instead of multiplying by 3 zombies per day, it's 85%. And so I can put in the 85% or show how I got it, 100% minus the 15% per day. So multiply by 85% per day. And then once you have that equation, you can go and answer the questions on the next page. At this rate, how long will it take scientists to completely turn all the zombies back into humans? So you can try that. And what are the similarities and differences that you notice? And what number in the equation impacts whether or not the initial value will increase or decrease over time? So let's go over that one actually. Let's look at growth versus decay, and then we'll summarize. So when the zombies were increasing, here's what the equation looked like. We started with 5 zombies and went up by 3 per day. But when it was decreasing, we had that 6,975,000,000. But we multiply that by that 0.85 because it was 85% per day. So it says which equation impacts the initial value will increase or decrease over time. It's going to be this number right here. If this number right here is greater than 1, it's going to increase. If this number right here is less than 1, it's going to decrease. And so we'll do a quick summary right here. Equation for exponential growth, we have y equals a times b to the x. For each of these, actually, a times b to the x. But for growth, this b value, this has to be greater than 1, and then it will increase. And for decay, this b value is going to be less than 1. And we should say absolute value of that. And so when this is 0.85, it went down. When this is 3, it went up. And then if we talk about what the graph looks like, well, this one will start out slow and increase pretty rapidly. And this one will start out, and then it will decrease. So there's our first day of exponential growth and decay, kind of just looking at this word problem and figuring out the growth and decay rates.